It's a pleasure to have Professor LesterMackey from Stanford to give this presentation, which is the part of the joint search between IDSS and EECS for the position and statistics. Lester is an assistant professor in Stanford University. He graduated from Berkeley in the PhD in computer science and undergraduate in Princeton, I believe, also in computer science. And he's a recipient of the Best Student Paper Award from International Conference on Machine Learning. And he's also interested in competing in prizes and winning. His team was the second place in the famous Netflix prize competition. And his team, another team and another project, he was received the first place in so-called Prize for Life competition for modeling in Lou Gehrig's disease. And today he's going to talk about matrix completion and matrix concentration. Lester, it's a pleasure to have you.
Thank you. Okay, can everyone hear me in the back? Yeah? Okay, great. So today's talk will be a talk in two parts. In the first part, I'll introduce divide factor combine, which is a parallel divide and conquer framework for either large scale or real-time matrix completion. And as we'll see, this framework relies heavily on matrix concentration inequalities for its analysis. So in the second part of this talk, I'll show you how you can use Stein's method of exchangeable pairs to derive such matrix concentration inequalities. So this is joint work with a number of wonderful colleagues, Amit Talwalkar, Mike Jordan, Richard Chen, Brandon Farrell, Joel Trop, and Daniel Paulin. Okay, so let's jump into part one. So the motivation for the first part of this talk is large-scale matrix completion. So our goal is going to be to estimate a matrix. We'll call that L naught. It's going to be an M by N matrix, given only a subset of its entries. Okay, so why that task? Well, this comes up in a number of settings. So let's imagine that the columns of your matrix actually represent users in your database, and the rows represent items that you could recommend to them. And you observe some of the preferences that those users have for those items. And you'd like to, so the numbers I've shown here are ratings that they might give on a 1 to 5 star scale. And I see that this user rated Legally Blonde 4 and rated Batman Begins 5. And I'd like to predict the unseen preferences. That is, I'd like to know what other movies would this user like. All right, and that corresponds to filling in the missing entries in this matrix, that is the large number of question marks that I haven't directly observed. So if you're a company like Netflix, you'd like to solve this problem at scale because you have on the order of 40 million users, and you have hundreds of thousands of movies and TV shows that you could recommend to those users. This is a large matrix that you'd like to complete. As another example, you might want to do ranking on the web. So you might observe the browsing and click history of a user, perhaps through news articles on Google News, and you'd like to predict whether a new article is relevant to that user. Okay, and if you're a company like Google News, again, you want to solve a problem at scale. You're dealing with millions of articles at a time and over 1 billion users. As a final example, link prediction in social networks. You might observe the friend connections that are formed on Facebook, and you want to predict what other sorts of connections exist between individuals that haven't been expressed yet. And if you're Facebook, and this number is probably outdated now, you have, again, a scalable problem with 1.5 billion users in terms of rows and columns. OK, so the good thing for us is that this problem has now been studied quite a lot. And so there are a lot of very good algorithms and a lot of very good theory surrounding this problem. In particular, there are many algorithms now that enjoy very strong estimation guarantees of the form, if I see a small fraction of the entries of a given matrix, I can actually complete the entire thing either exactly or very well, depending on the noise level in the problem. But many of these algorithms with these strong guarantees are actually plagued by very expensive subroutines. So for instance, they might have to perform a truncated SVD on this giant matrix on every iteration of a procedure like gradient descent, a gradient descent style procedure. And that makes them very expensive for these large-scale problems. So the question is, and the goal of this talk, is to present some divide and conquer approaches for scaling up your favorite matrix completion algorithm while still maintaining its strong estimation guarantees. OK, so let's go back to our goal. This is how I defined it. Given a subset of entries of your matrix L0, estimate the entire matrix. And in practice, we're not even this lucky. Because we don't see the real entries of the matrix, we see some noisy version of those entries. So this is what you might call the exact matrix completion problem. But we're going to be concerned with the noisy matrix completion problem, where you care about estimating a matrix L0, but what you observe are entries from a perturbed matrix, a matrix that has added noise, entry-wise added noise. We'll call that added noise Z. And the result, L0 plus Z, is a matrix M. And you're seeing entries from M, and you still want to estimate L0. We'll call that the noisy matrix completion problem. OK, so this problem is clearly ill-posed, right? If I give you arbitrary entries from an arbitrary matrix, there's no way that you can fill in the rest of the entries. That doesn't make sense. Anything could be in those entries. So we need some sort of structure to tie together what we see to what we didn't see. And so the structure we're going to use in this talk is a low-rank structure. So we're going to assume, in particular, that this matrix L0 has some rank, we'll call it R, that's much smaller than its ambient dimension, much smaller than M or N. So why is that good for us? Well, that's great because now L0 implicitly has many fewer degrees of freedom. Even though it's an M by N matrix, it only has something like MR plus NR degrees of freedom, because you can write it in a factored form in terms of a tall and skinny matrix and a long and short matrix. So that's the good news. The bad news is that not all low-rank matrices can be recovered. There's still some problems. Some things could still go wrong. So what can go wrong? Well, the first thing that can go wrong is that we might not observe anything about a particular user in our database, say. And if we don't observe anything about that user, even if our matrix is very low rank, there's no way to recover any information about that column, about that user. The standard way in the literature of dealing with this, for analysis purposes, is to assume some sort of observation model, like a uniform observation model. We're going to assume that for this talk. It's clearly too strong, and you can relax this notion to non-uniform row and column sampling. But the model is going to be that we observe a set of S entries of our matrix, and that set S, that set of S entries, we'll call it omega, is uniform across the matrix. All right, and this essentially will ensure that we observe every row and column. It's very likely that we'll observe every row and column under this model. Yeah?
Provided that S is large enough.
Provided that S is large enough, that's right. And that will come into the analysis. Right? So part of the analysis for the success of matrix completion that I mentioned actually ensures that S is large enough that you've seen all the columns and rows. OK, so that's one thing that could go wrong. A second is that you could have very bad spread of information in your matrix. So here is a very low rank matrix. It's rank 1. But in particular, it's a very interesting structure. There's a single 1 in the top left entry, and everything else in the matrix is 0. So rank 1 matrix, but all of the information in the matrix is in that one entry. So this is a 3 by 3 matrix, but imagine now it's your 1.5 billion by 1.5 billion matrix. And if you don't observe that single entry, that single 1, you're never going to guess that it's there. Probably your best guess is that there's a 0 in that spot, and you're going to lose. You're going to do a poor job of estimating that 1. OK, and the reason is that there's no indication that this 1 should be here in other parts of the matrix. The information is not spread out. To deal with this sort of problem, the standard solution in the literature, or a standard solution, is to assume incoherence with respect to a standard basis. You can just view that term as good spread of information. So it's worth noting that in this literature, it's good to be incoherent. OK, so what does that mean exactly? I've given you the exact definition here. But essentially, it says that if I take my matrix, it's low rank, and I take its truncated SVD, then the singular vectors are not too skewed. So they don't look like a 1 with a bunch of zeros. And they're not too cross-correlated with one another. But again, the notion you should have in your mind for the purposes of this talk is that incoherence means good spread of information. OK, so it turns out those are the only things that could go wrong. So let's figure out how we could actually estimate our matrix, assuming these bad things don't happen. So how do we estimate L0? OK, well, we know L0 is low rank. So what we might do is find the matrix with the smallest rank that matches the entries that we've seen. That seems natural. But remember, of course, we don't actually observe the entries of L0. We only observe these noisy entries of M. So you might say instead, let's find the matrix of smallest rank that is in a delta ball away from the entries that we see. That seems reasonable again. But this is a problem. This is hard. This is a hard problem to solve. It's an MP hard problem. So what could we do in practice? Well, we could relax the problem into a convex optimization problem. That's now a common thing to do. So we replace this rank objective with a trace norm objective, which is the sum of the singular values of your matrix. OK, so we could do that. And the questions you should be asking are, first, will this heuristic, what's called the nuclear norm heuristic, successfully recover the matrix L0? So does it do well? Is it a good thing to do? And second, will it scale to these large matrix completion problems that we care about? So first question, does it work? Does the noisy nuclear norm heuristic that I just showed you work? And the answer is yes, it does work. Or at least it works with high probability. And the sort of theorem you might see in the literature looks like this. There are various flavors of this now. It says that if L0 is rank R, and it's incoherent, meaning it has a good spread of information, and you observe your entries uniformly at random, and you observe about R times n of them, so R times n times some extra log factors of them, and you solve this heuristic, and you get back an L hat for your estimate, then L hat is a good estimate for L0 in the following sense. If the noise level in your problem is delta, then your recovery error is delta times some factor that depends on the dimensions of the problem. And that factor changes from analysis to analysis. Different analyses give you different results there. But this is the flavor of the result. That is, if your noise level is delta, your recovery error is scaling with delta. And in particular, this implies exact recovery in the noiseless setting. That is, even though I'm seeing only a small fraction of the entries, I can exactly recover my matrix using this heuristic. Yes?
So do I have to supply an upper bound on R for the algorithm?
It depends on the algorithm. But for this sort of procedure, you wouldn't, but you're just applying something else. So there's always something that you have to supply. In this case, it's delta for the noise level. In other variants, you have a regularized form, where your objective is a combination of the squared error and your trace norm penalty. And then some of these analyses actually tell you how to set the regularization parameter, and the guarantees are for that setting. So for instance, this Candes-and-Recht result, this Candes-and-Plan result says pick lambda to be 1 on root n, and you get this recovery result. So that's nice. Yes?
What kind of noise are we using? Is it bounded?
Bounded noise, essentially, yeah. If it's not exactly bounded, if you can argue that it's bounded with high probability, then that works out too.
But in this theorem, are you assuming that the true value lies within the...
That's right. It varies from analysis to analysis, but basically.
Universal constants?
They're not. I mean, this is meant to encapsulate all of these different results. So they're different for different problems, for different analyses of this problem, I should say. OK, that's a typical theorem. Basically says this works with high probability. So now the question is, does this scale well to the problems that we care about? And I would say the answer is not quite. So in these original analyses, the Candes-and-Recht analysis that kicked off this line of study, they suggested they said this problem is a semi-definite program, or can be represented in that way. If you use standard interior, you could just use standard interior point methods to solve it. Well, already that gets pretty bad scaling in all the relevant parameters, cubic and quadratic scaling. So let's not consider that. There are more efficient, tailored algorithms that you could use, like singular value thresholding, augmented Lagrange multiplier methods, accelerated proximal gradient methods. These are all more tailored, but they all also require rank k truncated SVDs on every iteration of a gradient descent style procedure. And that's what becomes expensive when you're dealing with really large matrices. So what's the takeaway from that short message? That It's that these provably accurate MC algorithms are still too expensive for these large-scale problems that we care about. So the question is, how can we scale up a given matrix completion algorithm and still retain these strong estimation guarantees that we love about these algorithms? So here's one way, one solution. It's a simple idea, and it's divide and conquer. What are we going to do? We're going to take this matrix M, and we're going to divide it into submatrices. I'll describe the specifics in a minute. But first, I'll give you a high-level outline. So we're going to divide it into submatrices. We're going to run matrix completion on each submatrix in parallel. And then we're going to use techniques from randomized low-rank approximation to recombine those estimates into a single low-rank solution, a single low-rank estimate of L0. So before I say what are the specifics there, let me just discuss the advantages of doing this. First, completing a submatrix is often much cheaper than completing the full matrix. That's where you get most of your gain. You can also carry out the submatrix completions in parallel. So you only pay the cost of the longest running completion. Excuse me. You can use this with any base matrix completion algorithm. So you could use it with these algorithms that have provable guarantees. But if you have another algorithm that has other nice properties, you could just plug that in instead and wrap this framework around it. And with the right choice of division and recombination, you actually can achieve estimation guarantees comparable to your original base algorithm. OK, so let me give you a specific algorithm here for divide, factor, combine. This is what we call DFC-PROJ. It involves partitioning your matrix and projecting. So in step 1, you're going to randomly permute the columns and randomly partition your matrix into a bunch of column submatrices. So we'll call them C1, C2, up through CT. You're going to complete those submatrices in parallel. So you get back a C1 hat up through a CT hat. This is where you get most of your reduction in cost. Because your matrix dimension is reduced, we expect something like a t-fold speed up per iteration. And you're also only paying the cost of the cheapest matrix completion problem because you can run these problems in parallel, or of the longest running but cheaper matrix completion problem. Finally, to combine these estimates, so now you'll have a bunch of low-rank estimates of submatrices, but together they might not be low rank. So what we'd like to do is project all the matrices onto a common subspace that represents, hopefully, the true subspace of L0. So we need an estimate of the column space of L0. And for that, well, one thing you could do is take the column space of C1 hat. Right? If you have sufficiently many columns, you might hope that this will give you a good estimate of the column space. So you could project all of your submatrix completions onto that single subspace and thereby recover a single low-rank estimate. So this is a pretty common technique for randomized low-rank approximation. And in this case, it has very low cost because each of these C hats is typically already in factored form. So doing this multiplication is very, very cheap compared to everything else that came before. Now you might wonder, why C1 hat? Why not C2 hat? Maybe C3 hat was the best. So for that, we actually have a secret fourth step, which is our ensembling step, where we actually project onto each of the subspaces in turn, average the result, and find a low-rank approximation to that result, the best rank R approximation to that result. All of that is very cheap because everything's in factored form to begin with. Each of the C hats is in factored form. And this does very well in practice. Yes?
How much better does the ensembling give you?
It can do significantly better. And we'll see that in a second. Yeah. OK. So before we turn to some experiments, let's just talk about whether this should work theoretically. And the answer, I would say again, is yes, with high probability. This does work. And here's a theorem that we've, from our work. It says, under the same sort of assumptions we had before, so L0 is rank R. It's incoherent, so it has a good spread of information. Now we need slightly more entries. Before we needed about Rn entries. Now we need something like R squared n entries. and we're able to sample a sublinear number of columns. So you can sample a number of each submatrix would have a sublinear number of columns in it. Then you still get an estimate like the following. That is, if your noise level is delta, again, you're scaling with delta. But before, we just had this f times delta in the result. Now we have this extra factor of 2 plus epsilon. So this is what we're losing by doing the divide and conquer, along with having to sample more entries of our matrix. So
Sorry, L is the number of columns per block, or it's the
L is the number of columns per column submatrix.
submatrix?
Yeah. So it's like n over t, if there are t submatrices. And so this says that it actually suffices to actually have a sublinear number of columns. So you can actually have your fraction of columns vanishing as n grows and still get this sort of guarantee. And again, you get exact recovery for the noiseless setting. So in the noiseless setting, even though you're dividing your problem up and solving separate problems, you can still exactly recover your matrix. Yes?
So this is with the same quantitative degree of incoherence as the previous result?
That's right.
Cool.
The incoherence parameter is the same.
I'm curious, so when you partition them into submatrices, then within submatrix, this number of sample, this S, the number of entries that you sample, might not be enough
Exactly.
to guarantee that you observe every column.
So the question is,
becomes sparser.
yeah, so the question is, the problem seems to become harder because you're dividing up your entries amongst the submatrices. So this in part, so part of the answer to that question is this is why we need more entries. This is why we have this extra factor of R here. That's part of it. And the other part is that because we're uniformly dividing up the columns, you're getting roughly the right number in each submatrix. So the two things that are going on there. Yeah. But you do lose something.
But in this regime, do you expect to be able to actually recover each one of the submatrices, or this is off the table?
So we do. I mean, you expect to be able to cover that well enough so that your combination will still be good. Yeah. So this is the number of submatrices is n over L. So L is the number of columns left in each submatrix, so it's n over L. Yeah. OK, and I should just highlight at this point that the analysis of this procedure, this theorem, relies heavily on these Bernstein inequalities for random matrices, which I'll talk to you a bit about in the second part of the talk. OK, so what are the proof ideas that go into this theorem? Well, first, if L0 is incoherent, that is, has this good spread of information, then its partition submatrices are also likely to be incoherent with high probability. That's one thing that we show. On top of that, you want to show that each submatrix has sufficiently many observed entries with high probability. And these two properties together tell you that your submatrix completion succeeds. That is, you'll do a good job at completing the submatrix. And then finally, you need that your random submatrix, that one of those submatrices, one of those C1s, captures the full column space of L0 with high probability. So that when you project onto it, you still get a good approximation. Yeah? In part, and also in part because you have a good spread across, because it's uniformly, you're doing uniform sampling and also uniform partitioning, so you're likely to have around the average number in each submatrix.
And now
Yeah, so you already have the average, roughly the right average number to begin with, but because the dimensions are decreasing, there's some other complicated, so that's why the entry number goes up a bit. Yeah.
In practice, it's kind of difficult to have every single submatrix have the exact same number of columns. Does that cause any issues?
It doesn't need to be. It certainly doesn't need to be the exact same number.
Okay.
And these sorts of things should be true. Also, you can incorporate slack. So we didn't analyze that directly, but it wouldn't be that big of a deal. If they're wildly different, then you might run into some other problems with.
No longer uniform.
Right, with distribution of entries, you might not have enough entries. Different matrices are harder to complete. Some matrices are easier to complete than others, depending on their size. That's true too. Yeah.
To use your low-rank recovery on the submatrices, do you use the same R?
So what we do, so often the algorithms we're using are often these trace norm penalized algorithms that have a regularization parameter. So we use the prescribed regularization parameter, but that modified for the dimension of the problem. So there's usually a fixed lambda that we plug in. It's given by the theory, and we actually use that lambda to.
You say that you're increasing R or decreasing it?
Let's see, we typically penalize less. So you have a bigger trace norm. So it's kind of like having a bigger rank. Yeah. Yep.
So why would it only work with one random submatrix?
Would this only work with one round of doing this, you're saying? Or?
One matrix, like choose random columns, just complete that one to find the subspace.
So that's good for the subspace, but then you still need to fill in the rest of the matrix. Yeah. So this last part is fine for you only need a single random submatrix to get a good estimate of the subspace, but then you need to know, how do I fill in the rest of the matrix? And that's where the other estimates come in. OK, and this submatrix analysis builds on the randomized L2 regression work of Drenaeus, Mahoney, and Muthukrishnan. And that says that column projection succeeds, and overall, putting those pieces together, the whole DFC succeeds. OK, so let's see an example. Here's an example first using simulated data. I'm showing you 3 curves. They're error curves. And what are we doing? We have random 10,000 by 10,000 size matrices. We're recovering rank 10 approximations. That is, L0 is of rank 10. We observe noisy entries. And we're comparing how well our base algorithm does to this divide and conquer approach as you increase the number of entries observed in the matrix. So y-axis is RMSE, how far off you are in your prediction of entries. The x-axis is the percentage of revealed entries. And what do we see? We see that for the base algorithm, that is the black curve, we have a breakdown point of fewer than 1% entries. So as long as you have more than 1% entries revealed, you're doing a good job at recovering the matrix at basically the noise level. For our methods, these are the blue curves, the breakdown point occurs farther to the right. That is, you need more entries to do well. The dotted curve is the DFC projection algorithm. The solid blue curve is the projection algorithm with this ensembling step. And what you see is that with the ensembling variant, once you get to about 3% revealed entries, you're basically getting the same error as the full base algorithm. But this is splitting into 10 subproblems, so you're doing it in about a 10th or the 9th of the time. OK, and just to highlight that, here's a timing curve. Here we have different size matrices that we're recovering. So up through 50,000 by 50,000 size matrices. And we see that the timing profile of the base algorithm in black is much worse than that of the blue algorithm, which again is getting comparable error because we're observing 4% of the entries. So we're seeing basically the same error level, but in much less time. OK, let's see a real example on collaborative filtering. Yeah.
Do you have a theory on the speed up? There should be some immediate bounce on the speed up that you get from this,
Well,
right?
it depends specifically on the algorithm. So yeah, so it depends quite intimately on the algorithm that you're using. So right now, you can plug in any base algorithm you want. We're plugging in a particular solver. It's an accelerated proximal gradient solver for that trace norm regularized problem. Each iteration does something like an SVD, a truncated SVD. So you expect maybe a t-fold speed up per iteration, but the number of iterations could change. Yeah. But I'll show you some timing in this example. So what's our goal? It's the one that I described to you at the beginning. We're given a sparsely observed matrix of user item ratings, and we want to predict the unobserved ratings. And there's some issues. The matrix we observe certainly is full rank. It's not low rank, but it's well approximated by the low rank matrix. We have noisy and very non-uniform observations, so some users are rating much more often than others. But we're still just going to apply our algorithm and see what happens. The data we're going to use is the Netflix prize data set. So this is 100 million ratings in 1 through 5. We have about 18,000 movies and about 480,000 users. And here's some results. So we're using a base method. That's the accelerated proximal gradient method. And I should just say right now that this is on random training test splits of the Netflix prize data set. So these are not at all comparable to the Netflix prize scores that you may have seen. Disclaimer. OK, so this is what the base method gets. It gets about 0.8433 RMSE on this data set. And it takes about 2,600 seconds to get to that point. All right, and this is still, it's a somewhat big matrix, but this is much smaller than the data that Netflix is actually dealing with. So what happens if we run divide, factor, combine? Well, if we run it with a division into 4 parts or 10 parts, we see that with 4 parts, we're getting about the same RMSE in about a quarter of the time. with 10 parts, the RMSE is starting to creep up, and we get about a 9x speed up at this point. If you add in the ensembling, with the 10-fold DFC problem, you're actually recovering the same error, but again, in 1/9 the time. And the reason why the time hasn't gone up for the ensembling is the ensembling itself is so cheap, the combination is so inexpensive that it's not reflected in the point-second scale. Yeah?
Can you offer some intuition for why DFC-PROJ ensemble 25% did better than
Did actually
ensemble?
better. This is something that we're trying to explore now. I think there's a lot in the power of the ensembling that's not being captured in our theory yet. And I'm thinking that actually ensembling even more than we are here could lead to just more accurate estimates overall. I could imagine something like carving up your matrix into lots of different submatrices of different sizes, getting lots of different estimates of those submatrices, and then combining them all would give you the best estimate overall. And I'd like to both see if that works and try to analyze that sort of thing. Yeah.
In the second line, for instance,
Yeah.
is the time running in 4 processes?
That's so. Yeah. So I ran all 4 of them in parallel. So this is the parallel single processor. Yeah.
What happens if you just parallelize that one and it's linear algebra, right?
So you'd have to parallelize your optimization algorithms. You could go through and.
Singular value decomposition.
So it's not a single singular. It's a gradient descent procedure. Yeah. So it's a gradient descent procedure where in every step you have some SVD in it.
Yes, snapshots on the small. So that's
So you can definitely insert parallelism into any given algorithm. I think the benefit of this is mainly that it's trivial parallelization, right? You're actually just solving your problems in parallel, which is very easy. Whereas these other problems require special case parallelism for your algorithm. So this particular algorithm uses truncated SVD in its intermediate steps, and there's some combination that goes on along the way. So only part of your algorithm is being parallelized. Like once you do your SVD, you're doing other operations on the, yeah. Oh, so this is all single core. Yeah, it's all, so the same algorithm is being run in all these cases, the same base method, and that base method is always using a single processor, a single core. That's right. So you could parallelize this base algorithm, and you could also parallelize the linear algebra in each of these DFC methods. Yeah. OK. So I just want to mention very quickly, some future directions, because I focused on matrix completion, but we're always looking for new applications and new data sets that could benefit from this sort of divide and conquer strategy. So structured recovery problems with some large-scale or real-time requirements. We've explored a couple of others. Video background modeling, that is background-foreground separation in video via robust matrix factorization, scaling that up. Image tagging and video event detection, so detecting whether a video is about a wedding or a concert on YouTube. We can speed that sort of process up as well. We're also interested in new divide and conquer strategies. So these would be other ways to reduce computation while preserving accuracy. To give you an example of another method that we can analyze, it's what we call the DFC-Nyström, so a generalized Nyström decomposition. So instead of just partitioning your columns, you can choose a random subset of columns, call those C, a random subset of rows, call those R, get an estimate for C and R in parallel, so recover their low-rank components, C hat and R hat, and then actually reconstruct the entire matrix just based on C and R. And to do that, if your matrix really is low rank and you're recovering the column space in C and the row space in R, you can use the generalized Nyström decomposition as your estimate for the whole matrix. This just involves estimating the overlapping column row subset of your matrix and taking its pseudo-inverse and then multiplying the products together, the 3 matrices together. And you can analyze this in much the same way that I described for the partition method. And if you want to do some secret ensembling at the end, you can imagine doing this many times over different column and row subsets and averaging the results. And that, again, helps. Final future direction, new theory, we'd like a finer grained understanding of the statistical implications of these divide and conquer algorithms. So what are the trade-offs between the statistical accuracy and the computational efficiency? In particular, can we say more about the impact of ensembling, which seems to play a really large role that we don't completely understand yet? part of what we're hoping is that these new tools that we're developing in the matrix concentration space will be useful for carrying out some of those analyses. And so I'd like to talk to you a bit about that to end the talk. Oh, yeah. Question?
So as I think about these methods, it seems that it would be very useful to be able to extend from matrices to tensors. Have you thought about that?
I personally haven't, but there are some folks who think about tensor completion in different settings. That is, in a sense, it's in a sense natural for the setting because there are other axes that you measure. For instance, time. The time of your rating matters a lot. And you can view that as a third dimension that would form a bigger tensor. And now you have a tensor completion problem. And so I haven't thought about it explicitly, but it seems applicable. So that could be an interesting application. OK, part 2. We have a little bit of time left. So in part 2, I want to talk to you about concentration inequalities for matrices. And when I mention concentration inequalities, I typically mean a quantity like the following that is a tail bound that controls the random fluctuations of a variable around its mean. So this is what I would mean in the scalar setting. And in the matrix setting, I mean something very similar. I want to control the fluctuations of a random matrix about its mean, where I measure the size of those fluctuations either in a norm, like the spectral norm, or in terms of an eigenvalue if eigenvalues are defined. And what do these give us? Well, these concentration inequalities give us non-asymptotic control of random matrices that have very complex distributions. So these are certainly applicable to problems like matrix completion from sparse random measurements, the problem we've been studying. But they've also been applied to analyze random matrix multiplication and factorization, to convex relaxations of chance-constrained optimization programs, and also to random graph analysis. So what's difficult about establishing a result like this? Well, I would say that the main difficulty comes from the fact that matrix multiplication is no longer commutative, which means that known truisms like e to the x plus y equals e to the x times e to the y aren't true anymore. And so past approaches at overcoming this have relied on deep results from matrix analysis, like the Golden-Thompson inequality or Lieb's concavity theorem. And they apply to sums of independent matrices and matrix martingales. In our work, we're taking a different tack that's based on Stein's method of exchangeable pairs as advanced by Sharav Chatterjee for scalar concentration. This gives rise to some improved exponential tail inequalities, like Hoeffding inequalities, Bernstein inequalities, bounded difference inequalities, to polynomial moment inequalities like Khinchin and Rosenthal, and to some inequalities for dependent sums and more general matrix functionals. So what I want to do in the remainder of our time together is give you a bit of background in notation, show you how Stein's method gives rise to some exponential tail inequalities, and then quickly mention polynomial moment inequalities and some extensions. OK, so some notation. From here on out, all of our matrices are going to be Hermitian. So they're going to be complex d by d matrices equal to their own conjugate transpose. All right, I'm going to use lambda max to represent the maximum eigenvalue of a matrix. I'll use TRB to be the trace of that matrix, the sum of the diagonal entries. And I'll use this unadorned norm to represent the maximum singular value of a matrix, the spectral norm. OK, so a key idea that we need to develop this work is that of an exchangeable pair. So if I have a pair of random variables, ZZ primed, I say ZZ primed is exchangeable if ZZ primed is equal in distribution to Z prime Z. And we need a special type of exchangeable pair called the matrix Stein pair. So let's imagine that you have your exchangeable pair ZZ primed. You pass each of those variables through a matrix function that spits out a matrix. So x is going to be that function applied to z. X prime is that function applied to z prime. And then we say that x prime is a matrix Stein pair if it satisfies this particular conditional expectation property. That is, the conditional expectation of x prime given z is a scalar multiple of x. And the scale factor there, this alpha, is called the scale factor of the pair. OK, so just to highlight a couple of things, because z and z prime are exchangeable, x and x prime, that's also an exchangeable pair. So matrix Stein pairs are exchangeable pairs themselves. And they also always have 0 mean because of this property, because of this conditional expectation property. OK, so why do we care about these matrix Stein pairs? There are a few reasons. So x is going to be our target. That's the thing that we want to master the concentration of. And it turns out that matrix Stein pairs furnish convenient expressions for the moments of x. So here's what I mean exactly. You might call this the method of exchangeable pairs. And it says that if I have an expectation that I care about for x, the expectation of x times some function f of x, then I can rewrite that expectation in terms of my matrix Stein pair. That is, I can exactly rewrite it as a function of the difference between x and x prime and the difference between f of x and f of x prime. So why is that good? It's good because expressions like this appear in concentration all the time. We care about moments of x, and sometimes we care about these exponential moments of x, like the expectation of x times e to the theta x. And this means that we can rewrite these expressions in terms of matrix Stein pairs, and then control the growth of these expressions in terms of the discrepancy x minus x prime and smoothness properties of your function f. So that's one good reason. The second reason is that these Stein pairs give rise to a measure of the spread of your distribution directly. So we need to define another quantity, which is probably the most important quantity of this part of the talk. It's called the conditional variance. And it says that if you have a matrix Stein pair, xx primed, and it's based on your exchangeable pair, zz primed, you want to consider the conditional expectation of x minus x prime squared conditioned on z. We're going to call that the conditional variance. It's rescaled by this factor. That's not that essential. We'll call that delta x. Why is that interesting? Well, delta x, you can view that as a stochastic estimate for the variance of x. Because of that method of exchangeable pairs lemma, the expectation of x squared is the expectation of delta x. So this gives you a stochastic estimate for how variable x is. And the take-home message, so if you take away nothing else from this part of the talk, it should be this one point, which is that control over delta x actually gives you control over the maximum eigenvalue of x. So if you want tail probabilities for x, you can look at delta x and show that it doesn't grow too quickly. So let me give you a specific example. It's going to be an exponential tail inequality for random matrices based on delta x. It says that if you have a Stein pair, a matrix Stein pair, and if your conditional variance is upper bounded by an affine function of x, so some function c of x plus v times the identity matrix. When I say upper bounding here, these are matrices, so this is in the positive semi-definite order. So the right-hand side minus the left-hand side is PSD. Then you get the following exponential inequality for the maximum eigenvalue of x. And what does this inequality say? It says that control over the conditional variance gives you a Gaussian tail for small t and an exponential tail for large t. When d equals 1, this actually reduces to the scalar result that Saurabh Chatterjee established for scalar concentration. But in general, this factor of d sitting in front, the dimension factor, is necessary. I mean, it only appears logarithmically in the quantities that you care about, but you need it in general.
The only randomness in delta x is z?
Z, which is kind of like x.
Kind of like x because, well, x is a deterministic function of z.
X is a function of z, yeah. So there's still randomness
It's
there.
almost sure with respect. Okay.
Yeah, so this is almost sure. OK, so what can you do with a result like this? This is pretty abstract. Well, you can use it, for instance, to derive a matrix Hoeffding inequality. So it says that if your random matrix is a sum of independent matrices, each one is mean 0. We'll call them YKs. Each one is mean 0, each one is bounded above by some AK squared. Then you can define a scale parameter, which is the norm of the sum of the bounds squared. And you get what you think of as a normal Hoeffding inequality. It says that the maximum eigenvalue of this independent sum is decaying like a Gaussian with scale parameter sigma squared. So there have been other matrix Hoeffding inequalities in the literature. This actually improves upon those. We get the optimal constant, what you would expect from a Hoeffding inequality, factor of 2 here. It turns out you can actually replace the scale factor with something even smaller. You could take the average of the bounds and the variances of your summands. So that actually is slightly tighter than the classical scalar Hoeffding inequality.
What is Z in this case?
For this example, what is this scale, the random scalar?
What is the Z?
Yeah.
So it doesn't have to be a scalar. It can be any random element. In this case, Z is going to be an entire vector of YKs. So Z is going to be your vector. So it's going to be YK, Y1 up through Yn. And we can talk more about the specific construction for this result, but probably afterward. So I could take you through the proof of this, but I'm thinking we're going to run out of time. So maybe I'll skip over that. There are only a few steps, and I'll just highlight the major steps. The first is relating the tail probability to something like the moment generating function of x. That's what we normally do for scalar concentration. For matrix concentration, we're going to relate it to the trace of the moment generating function. This was an idea due to Alsveda and Winter. It's a great idea, and most of the work in establishing matrix concentration inequalities of this form today involve coming up with ways of bounding this trace moment generating function. And in the past, people have done that using Golden-Thompson's inequality, Lieb's concavity theorem. Instead, we're using an idea due to Sharav-Chatterjee for scalar concentration. That is, we're going to control the moment generating function growth by bounding its derivative. It's something like what's called the Herbst argument. So I won't take you through all of the steps, but we use this method of exchangeable pairs to control the derivative of the trace MGF. We use some new trace inequalities that we derived to get a finer grained bound on that derivative. We ultimately end up solving a differential inequality, and that gives you the final bound on your tail inequality. So it is short enough that you could fit it into these 3 slides. So I encourage you to take a look at it after the talk. OK, so I just wanted to highlight that on top of these exponential inequalities, you can derive polynomial moment inequalities. So these have the same sort of takeaway, that is, moments of x are actually controlled by moments of your conditional variance. So if you want to bound the 2pth moment of x, you can upper bound it in terms of the pth moment of delta x. So this generalizes the Chatterjee's version of the scalar Burkholder-Davis-Gundy inequality. And the proof techniques are very similar to those for exponential concentration. One thing that you can derive from this sort of result, and I should just say at this point that while we've been considering matrices, these results also hold for infinite dimensional operators. OK, so one implication of that result is the matrix Khinchin inequality, which has been a dominant tool in applied matrix analysis used to analyze random matrix multiplication and also approximate singular value decompositions. And you recover that by specializing that last inequality, again, to a sum of random matrices. In this case, your random matrix sum is a set of deterministic matrices multiplied by Rademacher random variables, so random plus or minus 1 random variables. And you can upper bound its 2pth moment in terms of the size of those deterministic matrices AK. It turns out that there are other ways to establish this sort of result, but Stein's method offers an unusually concise proof with a constant that's within root E of the optimal constant. OK, so I just want to highlight some other things you can do with this technology, other inequalities that you can establish. I told you about this one exponential concentration inequality There's a refined version of that that gives rise to a matrix Bernstein inequality, and that relates the trace MGF, the trace moment generating function of your conditional variance, directly to the trace moment generating function of of x. So again, that conditional variance is key. And this also offers a tool for unbounded random matrices. You can deal with, we've been dealing with Hermitian matrices all this time, but that's not a big problem. If you have a general rectangular matrix, you can always embed it into a Hermitian matrix via a process called dilation. So if you have a rectangular matrix B, you can embed it into this Hermitian matrix where B is in the top right corner, its conjugate transpose in the bottom left corner, and zeros are in the diagonal, the block diagonals. And the maximum eigenvalue of this dilation is actually equal to the spectral norm of B. So you can gain control over the spectral norm of a general matrix by looking at maximum eigenvalues of Hermitian matrices. And finally, you can deal with, one beauty of Stein's method is that you can actually deal with some dependent sequences of random variables. So for instance, you can deal with combinatorial matrix statistics based on random permutations. So if you want to analyze sampling without replacement with better constants, you can get that for free using Stein's method. You can deal with dependent, you can derive dependent bounded differences inequalities for random matrices. And you can also deal, and we've been focusing on these particular matrix Stein pairs, which are exchangeable pairs with that extra property of conditional expectation matching. But we now have a way to deal with arbitrary exchangeable pairs. If you give me any exchangeable pair of matrices, I can give you a concentration inequality corresponding to that exchangeable pair. So you can actually move beyond the matrix Stein pair setting. And that's useful for deriving these bounded differences inequalities in particular. OK, so that's all I had to say. So thank you for your time.
We have time for questions. No?
Yeah.
Have you compared how this, the technique in the first part of your talk, how the performance compares with the SVD-based methods if you use like a randomized SVD algorithm?
So can you explain what you mean?
Well, so you showed that there were some other methods that you weren't considering that were SVD-based or based on the truncated SVD.
Oh no, we are using those algorithms.
Okay.
So what we're doing is using those algorithms as the base algorithms for our framework.
So then the question is how much composition do you get from speeding up the SVD using, say, a randomized technique or an iterative technique, and then applying this? Do these things work completely separately?
So how much speed up do you get from? Oh, are you saying take one of our base methods? Don't do your exact SVD in every step of that base method. Approximate those internal SVDs inside of the base method by a randomized SVD, and see how much that speeds things up. Yeah. Oh, so we haven't tried to do that. One nice thing is that if you have a way of doing that subproblem faster, you could still also on top of that plug your faster version of that algorithm into our algorithm and make it even faster. So you could do your randomized SVD and also do your divide and conquer on top.
Because if all you need is just a low-rank approximation, then you don't even need SVD. You could just do something like CUR, which is similar in spirit to what you're doing, where you're just picking random rows and columns to find a low-rank approximation for the problem.
That's right. We don't need an SVD at any point. And so an SVD is OK. So maybe when you say randomized SVD, you mean take your whole matrix and just do a randomized SVD on that. Yes. The reason why you can't do that is because it's not complete. So you're only observing like maybe 1% of the entries of your matrix. That's why you have to do these matrix completion procedures. So it's not just an SVD of your matrix. You still need to fill in all the missing entries. And so there's not a good natural way of doing a randomized SVD on your input space.
Well, maybe I'm misunderstanding something. I thought the point of the low-rank SVD was to construct such a structure for you to do the matrix completion problem.
So it's not a low-rank SVD. So there's no particular SVD. So OK, the problem is. We'll get back to eventually. So the problem is you're starting with a matrix, and you don't actually observe most of the entries of that matrix.
Right.
OK, so this is maybe a bit misleading. So you don't actually observe this blue square. You're observing a bunch of entries of that blue square. And so you want to find a low-rank matrix that approximates the completed matrix. And so what you're doing is completing each of the submatrices, and then from that, extrapolating into a low rank estimate of the whole matrix. And so you can't just do an SVD directly on this matrix because you haven't seen most of it.
Okay, well, maybe I'll take it offline, but I think maybe I'm just misunderstanding something on the slide just before this one.
Oh, okay.
Yeah.
Okay, I'll put it up.
Yes.
Yeah.
So
these involve truncated SVDs, but it's not of it's not of your input matrix. It's of some parameter in the algorithm.
oh yes, I understand. So the point is then, you could compute the SVD correctly for rank K, or you could do something cheaper and do a randomized SVD in those iterations.
Oh yeah. So then you have to so then you might wonder, is that algorithm still going to give you the right answer?
Right.
Yeah. So you have to analyze that too.
Yeah. So I was just wondering if you had thought about.
Oh, okay. We haven't thought about doing that particularly. Yeah.
Okay.
Yeah.
Go back, go on 20.
20. Yeah.
Okay, fine, right, back.
Yep.
Now, why is it that there's the same exact times for whether or not you do the ensemble?
Because this ensembling is so cheap. It's so cheap that it's less than 0.05 seconds, so it doesn't change the total time. Because you did most of the work already when you did your submatrix completions. The projection step is very, very fast because the matrices are already factored, and then you're just averaging. You're actually doing an averaging and a random projection, but all that's really cheap because everything's factored. Yeah.
Other questions? Yes.
So how would the DFC algorithm generalize to the online setting when you're getting streaming data as opposed to a batch matrix up front?
So that's a good question. So we're still relying on a base algorithm. So you would need something that's already doing online updating of your estimate. And it's not completely clear what that would mean because often those updates are kind of somewhat local.
Yeah.
You're only estimating, if it's in a single column, you're only some of your parameters are going to be updated. So I'm not sure. I have to think about that.
Okay.
Yeah.
I was wondering myself during the talk because it seems like you would have to, if you were splitting it up into a submatrix for every single, if you're doing the submatrix strategy,
Yeah.
and you try to do an online setting, it would kind of
You could try to upload just the relevant
Exactly.
submatrix and then combine. That's one way.
Yeah, but that seems a little bit hairy,
Yeah.
especially with the ensembling as well. So
Yeah.
Thank you.
Okay. Have we exhausted the questions? One more. Go ahead.
For delta parameter for the second part for the matrix concentration,
Yeah.
I was wondering, so I actually don't really have much sense on this, but is it usually easy to have a sense of what kind of bounds for the delta?
Well, so usually you're not interested in a particular. So usually you're interested in a result of this form. So where you just get a tail bound, and you see how it decays with deviation. And so one thing you can get from these inequalities is actually a bound on the maximum eigenvalue, like a bound on the expectation of the maximum eigenvalue. Often that's what you care about. The expectation of the spectral norm, the expectation of the maximum eigenvalue, and this gives you a bound for that. That's one of the main use cases. But otherwise, you want to see your tail bound decaying with the right rate depending on how many sum ends are in your sum. And we can talk a bit more about that offline.
And are these the bounds that you used in the first part of the talk?
We use these.
Needed to analyze the concentration.
We use these sorts of bounds. We use a matrix Bernstein inequality.
Bernstein. So you don't need to go to the elevated version that you proved, right?
So we have a matrix Bernstein inequality too, but so it's basically the same thing. Yeah, it's basically the same sort. We use a matrix Bernstein inequality, which we can also derive via these means. Yeah, there are other ways to derive it.
Yeah, that's awesome.
Yeah.
All right. Thanks very much, Leslie.
Thanks.